All right, so if you want to test the claim that the proportions for two groups are different, we would use the two-proportion-z test. And for the null and alternative hypotheses, the parameter is always the difference of proportions. The null value will always be 0. When it comes to a difference of proportions, the null value is always 0. So the null hypothesis is that the two proportions are equal to 0. The alternative is that the two proportions are not equal to 0. From there, we would collect the sample data. Again, this will usually be done for you. After that, we would check the conditions for check to see if the conditions have been met for the central limit theorem. And we want at least 10 successes and 10 failures for each group. We should have two different groups. We want to make sure there's at least 10 successes and failures for each of them. And we also want to check for independence for each group. That is, random selection, random assignment. We also want to make sure the two groups are independent of each other. The point estimate would be the difference of the two sample proportions. So the x1 over n1 minus x2 over n2. So the difference of the point estimates for the two groups. From there, we'd compute the standard error, which is square root of p1 times 1 minus p1 over n1, p2 times 1 minus p2 over n2. After that, we'd do the test statistic, which would be point estimate minus null value over standard error. The null value is always 0 for this test, so it's really just the point estimate divided by the standard error. Once we have the test statistic, we can use our calculator to compute the p-value using a normal CDF command. It'd be normal CDF, absolute value of the test statistic to 999.01 times 2. If the p-value is more than 0.05, we would fail to reject the null hypothesis. And that there's not enough evidence to go with the alternative. If the p-value is less than 0.05, we would reject the null hypothesis. That there's enough evidence that we should reject the null hypothesis and go with the alternative hypothesis. Now in R, we can run a two-proportion-z test using the prop.test command. The same command we used for the one-proportion-z test can also be used for the two-proportion-z test. Now, the tests that claim for the two proportions are different. We need to first look at the point estimates for each group. The x1 over n1 and x2 over n2. And specifically, we're going to separate those successes, those x1 and x2, and we're going to put the n1s together, the n1 and n2. So essentially how the command goes is we'll go prop.test, parentheses, and then x equal to c for that we're combining these, the x1 comma x2, and then the sample sizes, so the n1 and n2 would be the sample size of each group. And again, it's correct equals false. It really is an optional subcommand. I like to include it. The null value itself, if you don't include the null value in the command, the null value is assumed to be 0. So there's no need to include it with the command. Now the test is I'm going to use the PETS data set. So in 1991, researchers at the National Cancer Institute released the results of a study that investigated the effects of weed-killing herbicides on house pets. They examined 827 dogs from homes where an herbicide was used on a regular basis, diagnosis of malignant lymphoma in 473 of them. Of the 130 dogs from homes where no herbicides were used, only 19 were found to be found to have lymphoma. So my sample sizes, there's 827 for one group, 130 for the other group. In terms of the number of lymphomas, there was 473 in one group and 19 in the other group. Add this command to R. Again, use this read.csv command. This will load up this CSV file into R. The data set, if you saw, had two variables. One is herbicides, which records whether herbicides were used on a regular basis. And the other is lymphoma, that is, records whether the dog was diagnosed with lymphoma. So the population, this was dogs and homes. The sample self were the 957 selected dogs. This was an observational study. This was an experiment where we're giving lymphoma to dogs. Nothing like that. This is just an observational study. The specific variable interest is the difference in the rates of lymphoma from the homes with herbicides and the homes without. So we're going to compute the lymphoma rate for each group and subtract them. So this is a difference of proportions. Population inference cannot necessarily be claimed. The sample is fairly large, but the random selection was not mentioned. If it's not mentioned, we don't assume that there is random selection. So we can't assume population inference. Causal inference cannot be claimed because it's an observational study. Dogs were not randomly assigned to homes with herbicides and homes without. As far as the summary statistics, if I use the table command, I can get the contingency table. And you can see in the this first column, where there's no herbicides, I guess this first column is for lymphoma. Those that did have those homes that did not have herbicides, there was 111 dogs did not have lymphoma, 19 did. For the houses that did have herbicides, 354 dogs did not have lymphoma, 473 did. If you look at the Mosaic plot, back up. Look at the Mosaic plot, you can see this first column is this would be homes that did not have herbicides. You can see that bar is very large for the no's, not very much for the yeses. This other one's very wide because it's a much larger sample, but that was for the homes that did have herbicides. You can see there's actually more in the yeses for lymphoma. Looking at this, these two proportions appear to be different. So looking at this Mosaic plot, I'm going to guess that we're going to reject. Since we're testing whether the proportions are different, again, the null hypothesis is that the difference in proportions is equal to 0. The alternative is that the difference in proportions is not equal to 0. There was 957 dogs that showed that have these results here. The point estimate is the difference in the rates. So for the homes that did have herbicides, it was 473 divided by 827. For the homes that did not have herbicides, it was 19 out of 130. So if you go 473 over 827 minus 19 over 130, that's about a 43% difference between the two groups. Again, if you look at the table, there's at least 10 of everything. So there are at least 10 successes and 10 failures for each group, so the sample size is certainly large enough. Independence is a bit questionable. The results of the study cannot be extended to the overall population. So if we do have a result, it could be because of some bias with the selection method. We can't necessarily say this is true for dogs in general. In order to use R, we'll set X to be the number of dogs with lymphoma. So go back to the table. You see for the lymphoma, there was the 473 and the 19. So I'm going to let X equal to the combination of the 473 and 19. And it's going to be the sample sizes of the two groups. So there was 827 dogs in homes that use herbicides. 130 dogs that were in homes that did not use herbicides. Combine them, it'll be prop.test. We'll type X equals C, the 473.19. So these were the dogs with lymphoma. And then N equals 827.130. These would be the sample sizes for each of the two groups. I'll throw in the correct equals false. That part is optional again. And I get this result. So prop.test, there's command. And you see there's a bunch of stuff right there. A lot of it's stuff that we already typed in ourselves, we already knew. But specifically look at the p-value. Again, this p-value is less than 2.2 e negative 16. This is an extremely small number. Again, that e negative 16 means the decimal should be moved 16 places to the left. So we should reject the null hypothesis. There's strong evidence that the rates of lymphoma is different for the households with herbicides and households that are without. And if you want to do a 95% confidence interval, you can see that the difference in proportions is somewhere between 36% and 50%. So we are 95% confident that dogs in households with herbicides is between 36% and 50% more likely to have lymphoma than dogs in households without herbicides. So looking at this, there appears to be a pretty big difference in the two groups. Again, the way we have selection, we can't necessarily extend this out to everyone, to all dogs. But for this result, the results are pretty striking. I'll actually show you with R. I'll load up the data set. Okay. Let's see here. If I want to do a table of pets, there's the table. I can create a mosaic plot with mosaic plot, parentheses table, parentheses pets. You see right there, there does appear to be a pretty big difference between the two groups. Oops. What am I doing? All right, if I just want, come on. So if I want to just use that command, I'll just type it. Prop.test, x equals c, 19,473, n equals c, 130, 827. And what was that part? Correct equals false. Yeah. Okay. All right. Hey, see again the results. P-value very tiny. Confidence row I have negative. I must put it in different order. Yeah, I had 19,473 here. And here I have 473.19. So keep in mind the order. This one I had the dogs and households without herbicides first, so that's why I end up with the negatives. If I switched it, so the other one is 827, 130. You can see now these are positive.